Okay, buoyancy says that anytime you have an object that is either submerged or partially submerged in a fluid, so let's imagine we've got a boat here, and it's partially submerged in a fluid. What buoyancy says is that that fluid is going to push up on the submerged object. And the force, the buoyancy force, is going to be equal to the density of the fluid, not the density of the object, but the density of the fluid that's around the object, times G, times the volume that is submerged. Okay, so for example, with this boat, and actually, maybe the best way to say this is the volume of fluid that has been displaced. So, but that's the same thing as the volume that's underwater, the volume that, or the volume that's inside the fluid. So in this case, this volume, the part of the boat that's actually underwater, is the volume that's been displaced. And so the buoyancy force, this upward force from the fluid, is equal to the density of the fluid times the volume that's been displaced, that is this volume here, times G, the gravitational constant. So this shows up in lots of situations. Obviously a floating boat, or even just a floating piece of wood or a floating piece of ice. Right? So we've got this floating piece of wood, but it doesn't have to be floating, right? We could also have an object that's fully submerged, and there's still going to be a buoyant force. And in this case, the buoyant force is equal to the full volume of the object because the whole thing is inside that fluid. So this works for things floating in water or floating in mercury or whatever, but it also works for things that are in gas, because gases are also fluids. And in particular, there's a buoyant force for things that are in the air. A hot air balloon, for example, right, carrying people in it. The reason a hot air balloon can float is because there's air outside the hot air balloon, and so that produces a buoyant force that's equal to the density of the air times G times the volume of the balloon. Of course, there's also gravity pulling down on the balloon, but as long as the buoyant force is bigger than gravity, that balloon will accelerate upwards. And if the buoyant force is exactly equal to gravity, then the balloon can float. So, that is the idea of buoyancy, and I want to go ahead and give an example. So I'm going to do one where something is floating in air, or not floating in this case. So this problem says an uninflated balloon has a mass of 1.9 grams. So the idea is we've got this scale, and we've got this empty balloon, right? Like a birthday balloon, and it's empty, and we put it on the scale, and it reads 1.90 grams, and that's the mass of the empty balloon. Okay, if we then take that balloon and we fill it with argon, now argon is a gas that is heavier than air. So we fill this balloon with argon, and that gas is heavier than air. The question is going to be, what will the scale read? And we know that the density of argon is 1.66 kilograms per meter cubed, and the density of the air outside the balloon. So remember, there's also air outside the balloon. So this balloon is submerged. It is under air. It's not underwater, it's under air. But that still creates a buoyancy force, an upward force due to buoyancy. So let's think about all the different forces that are acting on that balloon. So there are actually 3 forces acting on the balloon. The first force that is hopefully pretty obvious is going to be the force of gravity pulling down on the balloon. The next force is this new force that we've just been talking about, the buoyancy force. That force is pushing up on the balloon. And then we've got the normal force from the scale pushing up on the balloon. And by the way, this normal force from the scale actually tells us what the scale is going to read. Now the scale reads in grams, but we're going to calculate the force in newtons, and then we'll see what the scale reads. Okay, the scale is calibrated to read in grams, so once we know what the force is, then we can figure out what the scale is going to read. All right, so in order to figure out the normal force, we're going to need to figure out the buoyant force, and we're going to need to figure out the gravitational force, but using Newton's laws, because this thing is not accelerating. So using Newton's second law, this should be equal to ma, and the acceleration is 0, and that tells me that the buoyant force plus the force from the scale is minus the force of gravity should be equal to 0. So the buoyant force, or the force from the scale, should equal the gravitational force minus the buoyant force. All right, so let's take a look at that. Gravity, we know, is supposed to be just mg. And you might think to yourself, oh, well, mass is 1.9 grams. But no, the mass is the 1.9 grams, that's the rubber, plus the mass of all the argon inside the balloon. So to figure out the total mass, we're going to need to add those together. So this is going to be the mass of the rubber plus the mass of the argon times g. So we know that the rubber is 1.9 grams, which is 0.0019 kilograms. And now we need to figure out the mass of the argon, and we're going to use the equation that density is equal to mass divided by volume. So mass is equal to density times volume. So the density of argon is given in the problem, 1.66. And now we need the volume. The volume is given in the problem too, and we were told that the volume is 2.5 liters. But a liter is 1/1000th of a meter cubed, and we need to convert that to meter cubed. So that is 0.0025 meters cubed. So that gives us a mass of 0.00415 kilograms times 9.81. Notice that the argon actually weighs more than the rubber balloon itself. Together, the argon was 4.15 grams, the balloon was 1.9 grams, and if we add those together, we get a total of 6.05 grams, which is 0.00605 kilograms, times 9.81, and this is equal to a force of 0.05935 newtons. So that is the gravitational force. Now to find the buoyancy force, we need the density of the air outside the balloon. Remember, when we're calculating buoyancy forces, it's the density of the fluid that you're floating in. So in this case, it's the density of the air times g times the volume of displaced air. That is the volume of how much volume is under air, how much volume is inside the air. And in this case, that's all of the volume. This entire balloon is under air. It's kind of like saying underwater, but it's not water, it's air. So the entire 2.5 liters is the volume displaced. So this is going to equal 1.20 kilograms per meter cubed times, of course, 9.81 newtons per kilogram times the volume, which is 0.0025 meters cubed. Remember that 1 liter is 1/1000th of a meter cubed, so we have to divide by 1,000 to get meters cubed. So the buoyancy force is equal to 1.2 times 9.81 times 0.0025. The buoyancy force is 0.02943 newtons. So notice that the buoyancy force is less than the weight. And so that means if I were to drop this balloon, it would sink because gravity is stronger than the buoyant force. But this thing has already sank, and it's sitting on the scale, and we want to figure out what the scale reads. So we're going to use that the scale reads gravity minus the buoyant force. So minus 0.0593. So I get that the normal force is equal to 0.02992 newtons. Okay, and on a normal day, that would be the problem. Calculate the normal force, and we calculate normal forces in newtons. However, scales read in grams, so we know this is equal to mg, and so if I divide that by g, I can find out that the mass is 0.00305 kilograms, and since the scale reads in grams, we can multiply that by 1,000, so the scale would read 3.05 grams. Okay, and so here's the deal. The empty balloon was 1.09 grams, and when we filled it with argon, it actually got a lot heavier. We could actually figure that out, right? The 4.15 plus 1.9, the total mass of the balloon filled with argon, the total mass of the balloon filled with argon was 6.05 grams, because we had 1.9 grams of rubber plus 4.15 grams of argon, and so the total mass was 6.05 grams, but the scale only reads 3 grams because the buoyancy force was lifting the balloon up. And because the buoyancy force was lifting the balloon up, we end up with the scale reading less than the actual weight of the balloon. Interestingly, if we filled the balloon up with air, if we filled it up with air, just regular air, it would still weigh 1.09 0.9 grams on the scale, because the extra air inside the balloon would add some weight, but the buoyancy force would be lifting up on the balloon just as much as the air inside the balloon is creating extra weight. And so if we fill the balloon with air, the scale would still read 1.9 grams. And of course, if we fill the balloon with helium, the balloon's gonna lift in the air, and that's because the air, the buoyancy force, would be bigger than the weight of the balloon plus the weight of the helium and the buoyancy, and it would just rise right up in the air. So here we go. That's how we calculate buoyancy forces.